Alright, let's get started with the quiz 5. I have a slightly different microphone than I normally have, so I hope the sound is alright. The first question is about Thomas Smith, and this is a waiting time formula. The first question asks, for one of his courses, Tom has to read a book. He can read 1 page per minute. His boss has agreed that in his idle time, he can study. The interesting phrase here is the important phrase here is the idle time. So we want to find out how much is the idle time. Well, to find what is his idle time, we have to first find out how much time he is busy. That is same as saying how much time he is utilized. Well, the formula for utilized, the easy one here to use is P by AM, but I'm going to show you the different method too. The processing time, it takes him 2 minutes to serve a customer, to handle 1 call, so it is processing time is 2. A is inter-arrival time, the call arrives every 3 minutes. Well, number of workers is just 1, so the utilization is 2/3. Well, if you want to find utilization a more traditional method, utilization is demand divided by capacity. Demand is, well, given that there is 3 units, 1 call every 3 minutes, there are 20 calls per hour. You could have done this for a minute too, but hours calculation is a lot easier. The capacity is the fact that he can answer a call in every 2 minutes, or it requires 2 minutes to handle a call. He can handle 30 calls per hour on average, right? So that means his utilization is again 2/3. No matter how you do it, you get the utilization as 2/3. In fact, you should get utilization as 2/3 or 66%. Well, now we are really interested in the time he is idle. That means he is idle 1 minus 2/3. That is the idle time, right? So that is he's idle 1/3 of the time. That is 33%. So he's given that he's idle 1/3 of the time, 1/3 of the 8 hours is equal to 2.66 hours. We can convert that into minutes. 2.66 multiplied by 60 equals to 160 minutes. That is, he has 160 minutes of free time. Given that he can read 1 page every minute, he can read 160 pages. A lot of calculations, but fairly straightforward. Right? Alright, let's get to the next question. How long does a customer have to wait on average before talking to Tom? This is a very typical TQ formula. In TQ, we have TQ equals to P multiplied by U 1 minus U multiplied by CVA square plus CVP square divided by 2. Well, P is easy, the processing time is 2. Utilization as we calculated is 2/3. 1 minus U is 1 minus 2/3 multiplied by CVA square is the standard deviation of arrival is 3. The mean of inter-arrival time is 3 squared plus standard deviation of processing time is 1. The mean of the processing time is 2. So 1/2. This whole thing divided by 2. Well, this is 2 multiplied by 2/3 divided by 1/3 multiplied. This is 1 square plus 0.5 square divided by 2. So this is same as 2/3 divided by 1/3 is 2 multiplied by 1 square plus 0.5 square is same as 1 plus 0.25, and this divided by 2. If you solve this, you should get 2.5 minutes. That is, every customer has to wait 2.5 minutes before they talk to Tom. Alright, the extra credit is not as hard as it looks, and I give a lot of hints too. So you calculated that a customer has to wait for 2.5 minutes. So the phone is on hold for that customer for 2.5 minutes, and 2 minutes of service time. So 2.5 minutes, and this is, let's make it slightly similar size here, and 2 minutes of talking time. That means a phone is in use for 4.5 minutes for every customer, right? For 4.5 minutes per customer. Now you want to find out how many calls he gets a day. Well, he gets 20 calls an hour, right? So in 8 hours he should get 20 multiplied by 8, that is 160 calls. That is altogether the phone is on use for 160 multiplied by 4.5 minutes, that is phone use. 160 multiplied by 4.5 is 720 minutes. Well, the phone is in use for 720 minutes. Well, 720 minutes is same as saying, something happened to my computer here, 720 minutes divided by 60, that is equals to 12 hours. So we know, I'm making too many errors today. Alright, 12 hours, the phone is in use for 12 hours worth of talk time. That is same as saying 12 hours multiplied by $5 per hour is $60 of cost. Right? Not as bad as it looks. So that was the only really hard question. The next question, the 50-step assembly line. This is the exact same problem that we did in class. So here, for a product to be defective, only if one step makes a mistake, it's really defective. So it's a linear assembly line. So we're going to find the yield of the process. To find the yield of the, in fact, we want to find the probability that a defective product is produced. So first we need to find yield anyway. The yield is, to get the yield, we multiply the yields of each steps. There are 50 steps, so we take the 0.99 to the power of 50. So given that it's a linear production system, to get the yield, we have to multiply the yields. So this comes to be 0.6050. And to get the defective rate, it is 1 minus 0.6050, which is 0.3950. The phrasing are different in the questions for section A and section B. So remember what is being asked. In one section I asked for the yield. In this section I asked for the defective product rate that the defective product is produced. If I had asked the yield, this is the answer. In this question is the rate the defective product is produced. So this is the answer, or 60.50%, and here 39.50%, depending on what I have asked. Alright, what's the probability a defective product is moved in the shipping line? Now here, this is a redundant process where if the product is if it is caught by one person, then it's good, right? So here the tricky part was, what's the probability a defective product moves to the shipping? So we already know it's a defective product. It's not so it does not involve the probability that the product could be defective, right? So it's we already know it's a defective, and then what is the probability it's gonna get caught is what the question is asking. So in this question, given that it's a redundant process, instead of multiplying the yields, we multiply the losses. That is, in this case, is 0.10 multiplied by 0.10, and we get 0.01. So the question only asked the probability of defective part moving out, the probability of the loss. So this is 1% is the answer. Had the product asked the yield, which would have done 1 minus 0.01, and it would be 99%. Again, if it's a redundant process, you multiply the losses and subtract from 1 to get the yield. If it is a linear process, you multiply the yields to get the yield. That's the only thing you need to remember. Alright, What is the capability score? The capability score CP is just upper specification limit minus lower specification limit divided by 6 sigma. This question is also different in the two versions of the test. The only real difference is in this question we have 0.25. Another section might have received 0.5 grams. Alright, but that should not change how you approach the problem. Upper specification limit is 95.5, lower specification limit is 94.5. Here the sigma is given as 0.25, 6, 0.25, and 95.5 minus 9, this is 1, divide by 1.5, so you have a 6 sigma, you have a capability score of 2/3. What is the percentage delivery is likely to be outside the specifications? Well, now this is the problem with the G. So our concern is the mean of 95, right? And then we are concerned with the values 95.5 and 94.5. So our goal is to find the equivalence in this standard normal, the mean of 0 and the sigma of 1. Here the sigma equals to 0.25. Similarly, we want to find the equivalence of 94.5. So let's call this G1 and let's call this G2. So G1 is equal to 95.5 minus 95 divided by 0.25. This would give you 2. Similarly, G2 equals to 94.5 minus 95 divided by 0.25. This would give you minus 2. Well, you can do so we are concerned the value outside these lines, minus G2 equals to minus 2, so this comes out to be about 2.28%. Well, you can do the math yourself, but as I know this is symmetric, I could just multiply it by 2 and get an answer of about 0.0456. Alright, to what level should the supplier have to reduce the standard deviation of the operation if his goal were to obtain a capability index of 2? So he wants a capability index of 2, and again he has to reduce the sigma to some value. So the formula is again Cp equals to upper specification limit minus lower specification limit divided by 6 sigma. We already know we want this to be 2 and we already know this is 1, right? And this is exactly what this is. Or 6 sigma equals to 1 by 2, or sigma equals to 1 by 12. So the standard deviation is 1 divided by 12. We would get a capability index of 2. Well, the next question is just routine calculation. There is not much to this calculation. The first question was, I asked you what is the mean and what is the average and the range for the fifth sample. According to my calculation, this has the mean is 351. All I did was took the average of these 5 values. The range is the maximum value 351.4 minus 350.6, which I got to be 0.80. Alright, so this was the answer for this question. The next question asks, calculate the x bar bar and r bar. Well, x bar bar is nothing but the mean of these 5 values, which I got to be x bar bar I got to be was 350.895. Range is the r bar is the mean of these 5 values. Some people made a mistake of again getting the range of the ranges. That's not what r bar is. R bar is the mean of the ranges. So don't take max minus mean here. Here we are just taking the mean of these 5 values, which I got to be 0.74. So x bar bar and r bars are 0.350 and 0.74. After that, making the chart, so let's make the x bar chart here. So this is x bar bar, whatever you got earlier here. Here the value 350.895, 350.895. This is x bar bar plus 82 r bar, and this is x bar bar minus 82 r bar. This is upper control limit and this is lower control limit. Well, the very value that's missing is a2. a2 comes from n equals to 4 because we have used 4 items in each sample. a2 for a2 for n equals to 4 is 0. Computer is trying to autosave every time. 0.729. So you can do the math. X bar bar, you already have it. A2, you already have it now. R bar is 0.74. So you can put this into equation as 350.895 plus 0.729 multiplied by 0.74. I got this value to be 351.4352. Similarly here, 350.895 minus 0.729 multiplied by 0.74. I got this value to be 350.3548. Well, to get the R chart, again draw the 3 lines. This value is given by R bar. The R bar we got was 0.74. This is given by D4 R bar. The D4 again for n equals to 4 is 2.282 multiplied by R bar of 0.74. I got this value to 1.6872. Here D3 R bar, D3 is 0. 0 multiplied by 0.74 is 0. That's all there is to these X bar and R charts. The last question is kind of was a tricky question. The statistical process control mostly helps. The real right answer is if the vendor performance is falling rather than if there is assignable cause is disturbing the process. If the assignable cause is deteriorating the process, then it will catch it. But disturbing doesn't always mean deteriorating for the most part in the true meaning. But I give I marked it as a correct answer even if you answered A or B. But in my mind, the real right answer is B. Alright.